Recording is rolling. It is Tuesday, August 19th. So I have a bunch of slides I'm going to go through today related to scientific method, measurement, a little bit of algebra, geometry. Now, planning ahead of time, but okay, I can probably knock that out in half an hour, and then we'll have some time left over so we can switch back and get from yesterday. We were doing this triangles and vector components and right and work on these. Now, how it's paced out earlier today is this ended up taking off class, and I still had a few more I wanted to go over. So, yeah, I think sometimes it'll work out like this. So, here I still got this original due date is this coming Thursday for that page pickup from you guys. So the trig lab and the 10 triangles. So we still got today and tomorrow, but yeah, I'll see how things pace out. Like if you have reasonable time to finish that by then. All right, so leave that there for now, but we'll see about that by tomorrow. Great. And again, yeah, thank you looking for to get you guys a quiz. I'm still looking at next Thursday, so Thursday the 28th. Every day after school, I'm going home, just looking at the videos that I put together for you guys, like I'm recording right now. Picking like one, two, maybe three questions that I think are relevant, and piecing the quiz together day by day. That's what I'm doing. Okay. Some other notes here. Uh, you guys know that open gate system, you guys come through every morning. So they need teachers to sign up approximately every week. So I am Friday mornings. So that's what I'm kind of going for. I'm signed up for a bunch of those. So if you don't see me Friday morning, right, or my first period class, I'm telling them I might be a minute late. So that's what's going on there. There is fast testing coming up. Now this mostly applies to 9th and 10th graders, but check the Excel file I posted to Google Classroom yesterday. If you're in 10th grade, you're probably on it. If not, then check with your teachers. There might be some one of your classes might be changed on Tuesday. So if that's the case, I'll probably tell you. And then tomorrow there's going to be an infrastructure. Oh, whoops! I didn't actually write that here. Here's for my other class though, guys. Tomorrow there's an infrastructure test during second period at 9:55. I think they'll come over the intercom. They're going to have everybody open up their laptops and try to get on the same side at the same time. I think they're just testing, making sure it's not going to crash the system. Okay, so just look for that in period 2 tomorrow. All right. All right. Any questions about the agenda? What we're doing? Agenda? Guys good? All right. So let's go through these slides. Okay. Again, you guys know that very first day of school, I gave you guys a whole sleeve of notes. Right. There's a whole packet of these thumbnail notes in here. Look like my posters hanging around my class. So I'm playing off those. All right. Let's start with the scientific method. Now I have 1, 2, 3, 4, 5, 6 steps here. Some textbooks have 5, some textbooks have 7. Okay, so yeah, all right. So a little plus or minus on this. Okay. So let's see if now what do I want to say about the scientific method before I reveal this? Okay. So a few things about this. So I'm gonna write down science. Okay. So when people talk about like science little quotes here, normally talking about like one of two things or a combination of things. There's a scientific method, which I think is the more important part of science. It's a process, so it's a way of thinking about this. And there's sort of like the book of science. Like, what are the results that come out of doing many, many scientific processes and experiments and results, blah, 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 right? Right. Now, the method's like a procedure that took people thousands and thousands and thousands of years to come up with. Right? Before science, they were processes of logic. They were, it's like sitting in an armchair thinking, well, I know A is true and B is true, so therefore C must be true, right? That's like the logic process. There's like other perspectives to see the world. You can see the world through maybe like a religious perspective, or through mythology, or through art, or that might be a little bit outside this, right? Right. Now, the book of science is all the facts that we've collected through this method, which is probably mostly true, but just as a matter of statistics, there are like certainly published articles that are just again matter of stats. Maybe we'll find, oh, actually, this isn't quite true. If you run this experiment, you can't replicate it, and then the scientific method is a self-correcting process. All right, so with all that in mind, let's go through this process. What do you guys think is probably a pretty good first step? Yeah, some kind of question. What is it that we're trying to find, right? Good question, right? What do you think is probably a good second step? Actually, before you, yeah, let's go with research. So I heard research and hypothesis. Yeah, again, probably depends what textbook you open. I'll put research here because if you have a certain question, there's a good chance it's been asked before. Maybe it's been approached before. Maybe you go read through the literature and realize, oh yeah, this experiment has been done 10 different times and they always got this result. Therefore, I can probably guess that's probably how it's going to work out. Maybe I can try to sort of repeat that experiment. Or maybe someone has an original approach to a question. I didn't even think to approach it that way. Like, oh, okay, that's an interesting way that's out there in the literature. Or that opens up a whole new possibility to kind of see what's around me. And then you guys said hypothesis, right? Hey guys, what is a hypothesis? That's a what?
Educated.
Yeah, okay, I like that. You said educated guess, educated guess, right? So, now, depending on exactly what you're trying to chase down, if you can put this like in an if-then statement, it's usually a little bit stronger. Like, okay, I think if I change this variable, it'll change this other variable this way. If you can quantify it, okay, that'll make a stronger hypothesis, right? Okay, so if I change this variable like this, then this other thing will change this way. And if I can quantify, for example, here, just to spitball an idea, what if I'm going to drop a ball off a cliff? So like this right here, I'm gonna go to the edge of a cliff and drop a ball. And maybe I want to know what is the crash speed at the bottom based on this cliff height. I'll call the cliff height h. I'll call crash speed v for velocity. So v for velocity, like how fast. Okay. Okay. Do you guys think that the taller the cliff, the faster the crash speed? I mean, that's probably pretty solid. You know, they did it. That could be a hypothesis, right? If I increase the height of the cliff, it's going to crash faster, right? But maybe I could quantify this even more specifically. Guys, what if I double the height of the cliff? If you double the height of the cliff, do you think the crash speed also doubles? Or more than doubles? Or increases but at less than doubles? Or maybe it doesn't change at all, right? What could that be, right? Now we're sort of more like quantifying. If I double the height of the cliff, then the crash speed will, right? What do you think? Right. And this brings me to another part of a correct scientific hypothesis. If you have a correct scientific hypothesis, should your hypothesis be something that is only ever verifiable or something that is only ever falsifiable? And only one of these is true. If you have a correctly modeled scientific hypothesis, is it only something that is only ever verifiable or something that is only ever falsifiable? Show of hands. How many guys think you want it to only ever be verifiable? Only verifiable. How many guys think only ever falsifiable? Only falsifiable. Yeah, here's my winners right here. Falsifiable. Yeah, falsifiable. Okay. So it goes like this. Suppose I hypothesize. Let's see if I drop the ball from twice. Let's say I double the height of the cliff. I think the crash speed is going to double. I think that would be my hypothesis. Well, that's something that I can test, and that might not turn out to be true. And if it doesn't turn out to be true, then I just falsified it. It's like, oh, yeah, I doubled the height of the cliff, and in fact, the speed changed, but it did not double. All right, so okay, so now I just falsified my hypothesis. Right? So you want to couch a hypothesis in a way that it can actually be tested, and it is vulnerable. It is open to being falsified. If you create a hypothesis that can only ever be proven true but can never be falsified, then that's not within the realm of science anymore. So what was my example for something like that? Oh, you guys ever heard of a term called confirmation bias? You guys ever heard of confirmation bias? Right? So this is how human brains tend to work, and it's just a human thing. Maybe it's more of like a lawyer way of thinking rather than the scientist way of thinking, right? But all of us have models for the world. We're all navigating our lives. Like, okay, I think this kind of works like this. I think this kind of works like this, right? And what your brain does, just human brain, just how it works, is your brain tends to hone in on facts about the world that support your pre-existing beliefs, right? And kind of ignore or explain away anything that doesn't quite align with that. Like, oh, okay, well that's kind of weird. That probably doesn't count. Or okay, well there's probably some weird that it just kind of shuffles it away, right? But if you're thinking scientifically, you really want to design your hypotheses, your ideas in a way that you can poke holes in them. You're trying to poke holes in them, right? If there's some phenomenon, there's like 10 different ways it could work, right? So if I increase the height of this cliff, right, does the speed how does it vary with the cliff height, right? Maybe there's so many different models that could work, right? And by testing this out with data, I can falsify all but maybe one of them. So whatever's left is probably the answer. All right. What's a good step after hypothesis? Yeah, let's do experiment. Yeah, test, experiment. Okay. And if you design a correctly designed experiment, now I'm thinking of different kind of variables. What are different kind of what's one kind of variable? Yeah, independent. Independent variable. What's another type of variable? Yeah, dependent. Okay. And what are these? Guys, if something is an independent variable, what does that mean? Okay. Yeah, and you're saying, okay, that's something that you're directly changing. Like with my cliff and ball example, that could be the height of the cliff, right? So if I double the height of the cliff, that's something that I'm changing myself, right? The dependent variable is whatever a variable that changes in response to that. So if I'm testing this crash speed right here, right? This crash speed, right? That could be my dependent variable, right? And that crash speed looks like it's dependent on the cliff height, possibly, right? Maybe I can test that up, right? But there might be some other variables. Like, guys, what about this? What if I change the cliff height, but I also change planets? What if I have a short cliff on Earth and a tall cliff on Mars? Am I getting too many variables going on now? Yeah, right. Because I don't want to change the height of the cliff and also change the gravity field. I want to keep some of those variables, what starts with a C? Controlled or constant. Constant or controlled, right? I'll put controlled here. So it's like controls, right? So there might be like 10 different variables at play, but ideally, you want to have how many independent and dependent variables at a time? Yeah, one and one, right? So you want one of these and one of these, ideally, right? And then leave everything else controlled. So if you have, right, like in a few days, I'll have you guys roll Hot Wheels cars down inclines. And some of you guys are going to be testing, measuring like how far did the car roll, or how much time did it take to roll down. You could change the angle of incline. Well, we're all stuck on Earth gravity. Can't really change that. Some of you guys will have you guys taping lab weights to the cars, maybe changing the mass of the car. Some of you guys have you used these speed gates. Watch this, guys. Watch the speed gate. Now, this says so many meters per second. Now, there's a couple little sensors right here. So if I swipe something through, swipe something through a fast. Yeah, it usually works with the sound effect. That's right. Oh yeah, 2.56 meters per second. You see that? Just like zoom through. So, and this car fits right through. Look at that. So when you have the car on the track, it'll go right through. It'll tell you exactly how fast the car's going. Okay. Okay. Now that's a lot of variables. Is what I'm trying to get at here. So you want to control everything except for change one independent variable and have one dependent variable changing as a result. Now, in the real world, sometimes this gets kind of messy, especially if you have big, complicated systems and you only have like one of them. For example, if you're an economist. Now, economics is a type of science, but it's like, sometimes kind of hard to tease apart data in the economy. It has like 100 different variables going on with it. Or like climate science. Again, we only had one Earth to work with. So you can have like, oh, I have an Earth over here and a parallel Earth over here, and let's see what happens if we only burn coal on this planet. Like, well, okay. But after experiment, what's a good next step?
Analyze your data.
Yeah, analysis. Got it. Analysis. Okay. Now, in an AP sense, this normally involves graphs. So maybe I'll graph on a y-axis versus an x-axis. Let's take that ball and cliff example, okay? Which is going to be really similar to what some of you guys do with these Hot Wheels cars. What if I have different cliff heights in maybe meters? So I have a short cliff, a medium cliff, a tall cliff, okay? And I'll say what's the v velocity, like the speed in meters per second. So maybe like does it crash kind of slow, medium, fast? Okay. And what does this relationship look like? Is it a direct relationship? That's say if I double the cliff height, I double the speed, or does it kind of bend down like this? Maybe if I double the cliff height, the speed increases, but not as much. Or maybe does it bend like this? Do it increase the cliff height and then it's like really slamming really fast? Right. Or maybe it does. Maybe it's constant. Maybe I increase the cliff height and the speed doesn't change at all. Right. I mean, any of those are possible. Right? Maybe I increase the cliff height and it lands slower. I don't know. Maybe. And what's the last step? Conclusion? Yeah, conclusion. Okay. And whenever you get to a conclusion, make sure that it answers the question that was being asked to start with. Right? You guys good on scientific method?
Yes.
All right. Got next here. Right. So how do you measure things? Measure. Right, so start with these three. Guys, kilogram could be a measure of what?
Yes.
Mass. Okay, this is this guy right here. Okay. What does M stand for as a unit? Meter, right? Like, I have a meter stick right here. It's in this meter stick, 1 meter long. Right. It's about 3.284 tiles. Right. And what does S stand for as a unit? Second. Right. Here's your stopwatch right here to measure time in seconds. Something like that. Right. Now, in the like 500 years ago, pretty much every locality, maybe every country would have its own system of units, but then it's kind of hard to compare. You get hundreds of systems all over the world. Okay, so around this time right here in history, let's do a little history right here, 1790s, right? And this system called the metric system comes around. We say, okay, let's standardize everything. We'll do everything base 10, so we don't have these weird conversions like 5,280 feet a mile. Yeah, that sounds about right. Right. So everything's gonna be base 10 conversions. Everything, all these units are gonna be related to each other, and everything will be standardized so that no matter where you are in the world, there's like a universal way to sort of reconfigure these units. Okay. Because what country does the metric system come from?
Is it France?
France. Yeah, France. Yeah. And what was going on in France in the 1790s or so?
The French Revolution?
French Revolution. Yeah, you guys remember the chop chop? So say, okay, let's have some reorganization here. We're tired of starving. Let's make our system of government look more like the Americans. And let's while we're at it, let's also reform a bunch of other things, including our measurement systems. So where do these come from? Actually, I should really start with meters. So where does this meter stick come from? So the original definition goes like this. So they started measuring from the north to the south coast of France really carefully. And so let's extrapolate that around the world. So if you go from the North Pole down to the equator and divide that into 10 million parts, you get exactly one of these. That's the original definition of a meter. So now, no matter where you are on the planet Earth, if you can kind of measure the curvature, you can figure that out. Okay. Oh, no, if you take a little tiny box, let's say 1 centimeter by 1 centimeter by 1 centimeter, and you fill that with water. Yeah, a little tiny. You guys see this little tiny box here? 1 by 1 by 1 centimeter? Right. Guess how much mass that is?
No.
Okay, that's a volume, 1 milliliter of volume. And if that's water, okay, that's 1 gram. That's 1 gram. Okay. Now that was such a tiny amount of mass. They said, okay, as a base SI unit, let's increase that by a factor of 1,000. So guys, what if I do 10 centimeters by 10 centimeters by 10 centimeter box? You guys see this nice hefty box right here? We fill that with water. And I hold that. How much does that?
1 liter?
1 liter of volume, but how much mass is that?
1 kilogram?
1 kilogram. That's this right here. That's this right here. It's the same mass. That was the original definition. Right. And then right. Now guys, this is the only base SI unit that has a prefix baked into it. You guys see that K right there for kilo? Guys, what kilo? What does that mean? That's 1,000, right? 1,000, right? So a kilogram is 1,000 grams. Now, later on, when we start combining these units and make composite units, for example, a unit of force, like how hard to push on something, that's going to be measured in newtons, or like these spring scales. If I pull on this, guys, can you guys see an N right there, capital N for newtons? It tells me right now I'm pulling with about 8 newtons of force to stretch the spring inside. Okay, that turns out to be kilogram meter per second squared, and that'll make sense in a few weeks as this class goes on, right? So like a unit of force, you need to combine these, right? But the point I'm trying to make here is that kilogram is a unit, right? It's baked into the cake of complex composite units, right? And what is 1 second? Well, let's just take 1 Earth day, divide by 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, right? Now the French also tried to make this base 10 and said, hey, let's have like 10 hours in a day and 100 minutes in an hour, and so that was too weird, so that didn't stick. But everything else pretty much standardized base 10, right? Right. So I do want to pass this around so you guys can feel this. I think you guys did the other day anyway. Right? But I want to make a point before I do. So you guys see what I'm doing right now? I'm pushing this back and forth. Do you think it take to change its motion? Do you think it takes some force to change its motion? Right. And okay, so when this is in motion, it has what's called inertia. Like it wants to just keep going. Wants to just keep going. Has some inertia. And it's hard to change its inertia, hard to change its state of motion. All right, you guys ready for a real tricky question? What if I take this to the moon and I have a table on the moon? Now the moon has a little bit of gravity, so this sticks down to the table, right? And I start doing this on the moon. Is it equally difficult to do this on the moon as it is right here on Earth? Does it feel exactly the same? How many of you guys say yes? It feels exactly the same to do this on the moon as it does right here. Winner. Winner, winner. Yes, it does. Yes, it does. It feels exactly the same, right? Because is 1 kilogram on Earth the same thing as 1 kilogram on the moon? Yes, it is. Yes, it is. Right? Now, you might be thinking, what if I pick this up? Now, guys, if I pick this up, am I lifting it against a gravity field? Oh. Yeah. Now, that's not mass. That's what starts with a W.
Weight.
Weight. right, was a type of force, right? Now to pick this up, it turns out it takes 9.8 newtons of force to lift this. Sometimes I'll just round that to 10 newtons. It takes about 10 newtons to lift this right here as I'm doing it in front of you, right? And if I take this to the moon, does it take more than or less than 10 newtons to lift it?
It's about 3.
Yeah, a lot less, a lot less. I think it's like 1.67 or something like that. 1.6 something. Okay. But yeah, so this has a lot less weight on the moon, but the same mass, the same inertia. So this feels the same on the moon, and this is different. You guys got that? Okay, the difference between mass and weight. Now pass around that kilogram. You guys get to feel that. Get your hands on that. All right, are you guys good with these three? Okay. Now again, we'll combine these to make all different composite units. Can I make volume out of just meters? Meters times meters times meters makes the volume. Can I make speed out of meters and seconds? Like meters per second, kind of like miles per hour, meters per second. Force, I told you guys, was kilogram meter per second squared. That'll make sense in a few weeks. Energy, energy. Did you guys eat lunch earlier today? Have some food calories? Okay. And the metric system that quantifies is kilogram meter squared per second squared. And that'll make sense in a few weeks. Okay. Right. Can you guys think of some things? I wonder what else is measurable in the universe. Guys, let's expand our thinking a little bit. Can you guys think of something you can measure? And I'm thinking of 4 things specifically. 4 things that you can measure that are not on that table. 4 things that you can measure that are not on that table. Okay, oh, here's time in seconds. Volume can be meters times meters times meters, so cubic meters. Volume. Gravity field. Turns out it's meters per second squared. Yeah, it's like Earth, we're in 9.8 meters per second squared. Moon's like 1.6 something meters per second squared. So that's also on here.
Wait.
Okay. How loud a sound is well, musical frequency note might be like 1/seconds. And how loud is it? It's like you can either put in pressure or intensity, which you can also make out of these. Okay. How about let's see. We got the answer on the next page here. How about this? You guys ready for lights? Lights. What am I changing in the room right now? Brightness. Can I call it maybe luminosity? Right? That's not captured in kilograms per meters per second. Ooh, hey guys, what's powering the lights right now? Some kind of
Electricity.
electric current. Right? How about is anybody wearing a jacket in here?
No.
And if you were, then because it's very,
Old.
which is the type of, what am I trying to quantify? Temperature. Right, here, guys, here's the full list. Okay. So kilograms for mass, meters for length, seconds for time, amperes for electric current, right, which is like coulombs per second, charge per time, kelvins for temperature, and if we do anything with this, it'll be the Kelvin scale because that goes all the way to 0, perhaps at 0. Candelas for luminosity. If you buy a bike light, it might be listed in either candelas or there's a similar concept called lumens, which is a little bit different, but right. And then hey, you guys have chemistry? Can you guys count in moles? Right, it's just a big number to count. All right, you guys good with those? Yep.
So like mass is not the same as weight, and so like mass will always remain the same. Like
Right. Yeah. So mass. Yeah. Let's go back to mass and weight. Mass and weight, different concepts. Yeah. So mass is like how much material, how much inertia. That's like if I'm doing this. Yeah. Weight is a type of force. Yeah. So if you pick something up, it's a type of force. Like there's gravity force pulling down. Hey guys, what if we were in the International Space Station, right? And we took out some tennis rackets and started bouncing this back and forth. Boing, 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 boing. Right? Would that feel a lot like it does on Earth? Bounce this back and forth? Yeah, because it still has the same mass, even if it's floating around in space. Has no weight. If you're out in deep space and it's just floating around with 0 weight, it still has mass. Guys, what if we're floating around in space, right? And I throw both of these at you? Which one do you want flying at your face? The little one or the big one? Yeah, let's go with the little one. This one's probably easier to stop in space, in deep space. This one has a lot more inertia. This one a lot more half points hitting you, right? Okay. Even if it has no weight. All right. Boing, boing. Now, the modern definition of all these are no longer material. Here's a little history too. So once these were established back in the 1790s, there was like a physical object that was like Le Grand Cup, the Great Kilogram, and it was kept in a warehouse in Paris. and there were physical rods that were a meter long, right? And those were kept in a warehouse in Paris. Now they checked them every so often. They would pull them out and there would be these weird variations that nobody could really explain. I don't think they cleaned off all the fingerprints and all the dust, and they would vary a little bit. So they're trying to get away from physical objects, and they just completed this project within our lifetimes. So now the modern day definitions of kilogram, meter, and second, and all these things are now based on universal constants. For example, the speed of light is the same everywhere in the universe. They're really trying to universalize this. You could go like halfway between the galaxies, and this is still the speed of light. Okay. Okay. So the modern definition of 1 meter is actually the speed of light multiplied by a tiny, tiny, tiny time interval, which is based on the vibration of a cesium atom. Okay, so all right, that's just a little extra right there. All right. Now let's look at measuring tools. Measuring tools. Which, by the way, head a little bit. When you guys get to the AP exam, one of your free response questions, they will want you to design a lab experiment, do a lab write-up. And one of the questions is going to be, what tools are you using to measure what variable? And this is your go-to list right here. So let's run through these. A meter stick or a ruler for displacement or length or distance. Okay, you guys can measure how long something. Could you guys use a protractor to measure an angle? Like how big is a wedge? We were just doing that yesterday, right? Do that with these wedges right here, these angles. Do that. Could you guys use a stopwatch to measure how much time? Maybe has your Hot Wheels car been rolling down an incline pretty soon, a few days? I forgot to drag this one out. Okay, guys, there's something called a motion detector. I don't have it within reach right now, but it's like this box. I always have trouble getting it working, but I'll see if I can pull this out in a few days. You can hook it up to your laptop, and it should tell you if a car's going straight towards it or straight away from it. It should tell you something about how far it's moved, how fast it's moving, and also something called acceleration, which is the rate that it's speeding up or slowing down. Okay? Okay. Again, I always have trouble using it, but you guys. Yeah. And then on the AP exam, you can talk about a motion detector, but don't ever talk about the speed gate. Did I show you guys the speed gate working earlier? Right, car goes through it. 0 tells you how many meters per second. Okay, because AP doesn't know that this exists. Okay, but I'll give you guys this in the speed gate. Okay. Oh, scales. So I do have a digital scale here. So let me turn this thing on. And put this up. Now this will tell me how many grams something weighs. Okay. Now what it's really doing is it's measuring a downward force, and it's dividing by Earth's gravity field and telling me what mass would it produce. Blah blah blah. I don't know if you guys can read this. Well, okay. It was saying. Yeah. Try this one more time. It says like 4.2 grams. 4.2 grams right here. Okay.
We have more time to finish the work.
Yeah, I'll find some more time at some point. Yeah. Today, okay, we're just doing this today. Okay. Right, so, now that's with the digital scale. Now, again, it's directly reading a force, but it's dividing by a gravity field to get what mass would have produced that. Have you guys ever seen a triple beam balance? Right, I was trying to dig one out this morning, but it disappeared somewhere. I'll see if I can find one. Right, but it works on a seesaw type system. Now, the nice thing about a triple beam balance is that you could use this on the moon in a different gravity field, and it will still give you an accurate mass reading. Right, so say about pull up spring scale. This can be used to measure a force. You guys see it says how many? You guys see capital N for Newton. So I can pull with like 6 newtons, 8 newtons, 10 newtons, right, to stretch the spring on the inside. There's a real thick spring in here, right here. Okay. Right. Spring scale. Got a couple spring scales here. Use those. Right. Okay. Force probe can also measure a force. Right. Similar idea. Maybe you can push or pull. Right, and these last two you aren't going to use for this class, well, at least not on the exam. All right, voltmeter and ammeter. So I do have a battery tester. Maybe I'll pull that at some point. Do you guys know how many volts is a AA battery? How many volts is a AA battery?
Is it like 6?
So it's like 1.5. Okay. Now you can stack them on top of each other, and you can make 6 and 12. Okay, but they're increments of 1.5 volts. Okay. Okay, and then if you hook that up to a circuit, you can get electricity flowing. So we'll do a little bit of electricity next semester, but not on the exam. Okay. All right. When you guys do your free response question for a lab write-up, there's a specific format that AP is always looking for. So I'll go over this with the guys, but this is also in your thumbnail notes I gave you guys the first day. So okay. So they'll throw some question at you, and then they'll want you to design your own experiment most of the time. So you have to come up with a list of measuring equipment. And we were just looking at that list. Okay. Right. Or sometimes they'll tell you you can only use a stopwatch or something. Okay. Right. Procedure. So they want you to briefly describe the setup. So if you're sending this Hot Wheels car down an incline, I'll have you guys do this in a few days. You say, okay, I'll set a car on an incline at so many degrees from the horizontal and let it go. And that's it. That's the entire setup. Okay. Then what measuring tool to measure what variable? And you guys are actually going to be doing a few different experiments, well, depending on what group you're in a few days. So some of you guys are going to say, how fast is the car going as a function of rolling distance? Some is how fast is a function of time. Some are going to go time and distance. Some of you guys are going to put some live weights on the car and say like how much time does it take, you know, for different mass cars, right? But of course, we'll narrow that down. What experiment are you doing exactly? Identify what is your independent variable, what is your dependent variable, what is everything else you're controlling, because you don't want to change too many variables at a time. Okay. And then AP's always looking for you guys to mention do multiple trials to reduce experimental uncertainty. So you don't want to just do one and then take that to be the truth. You want to do like at least 3 trials and take an average. Can you guys do that? 3 trials and take an average. And then of course put that in your write-up, and that's always worth 1 point on the AP exam. Okay. Analysis. They always want you guys to make graphs. We'll do lots of graphs in this class. Look at different graph properties. What does it mean? Okay. Sometimes just solve an equation. Okay. And then whatever conclusion you get, again, make sure that it's answering the question that was being asked to start with. Okay. Okay. You guys have this. This is part of your thumbnail notes. It's okay, guys. It's right. It's right here. Okay. It's right here. If you saw right up. Okay. Ooh. Scientific notation. What if I want to make very large or very small numbers? Do you guys think one of the calculations you'll probably make somewhere along this class is the moon orbiting the Earth? And that could depend on the mass of the Earth. Right? Here's the mass of the Earth in kilograms. Like, how many kilograms is the mass of the Earth? Oh, here it is right here. It's 5972 and a bunch of zeros. We got 3, 6, 9, 12, 15, 18, 21. There's like 21 zeros after these other digits. Okay. Now, do you want to go type in this in your calculator to figure out the orbital speed of the moon? Like 0, 0, 0, 0, 0. Do you want to do that? No, because wait, did I miss that 0? But wait a minute. Do I even know that this 0 right here is exactly a 0? This is, or all these zeros just acting as what? Placeholders. Yeah, placeholders. Okay. So there's a much more efficient way and also a better way to communicate this number. And guys, how do you write that?
5.9 times 10 to the, I don't know how many zeros and 972s are there. So the number.
Yeah, guys, try it out. Write it in your notebook. I want to make sure that you guys can communicate from your brain to your hand to your paper. Right, guys, write your notebook. Write that in scientific notation. This big old number. This is how many kilograms is the Earth. Write that in scientific notation. There's 21 zeros, but there's also these 3 digits after the 5.
I think I found the answer.
Yeah. Okay, guys, what did you guys just write?
Anything up on the board?
5.9. 5.97 times 10 to the what? 24. Yeah, there it is. Right. So you're multiplying by 10. You're doing that 24 times. That's what 10 to the 24 is, right? Except, right. Also, this tells you something else. Okay. Because guys, going back to the original expanded form of the number, is this 0 right here? Is this also a placeholder, or do we actually know that this 0 is a true 0? Well, it's kind of ambiguous if you write it out. Maybe they do know that the 0 actually is a 0, or maybe it's just a placeholder. And how would you know? Well, in the expanded form, you don't know. But in scientific notation, you know every time. Now, guys, the way I wrote it, is this 0 acting as a placeholder, or is it actually a 0? Yeah, it's just a placeholder, right? But what if I took my time to write a 0 right here? Then would I be communicating to whoever's reading it that I know that that next digit actually is truly a 0? Yeah, I would know one more level of precision. Okay, you guys get that? Yeah. How about let's go small? Can you guys go small? What's the mass of a proton? Okay, well, there's the mass of a proton in kilograms. Right, so 0. Got 3, 6, 9, 12, 15, 18, 21, 24, 35, 26, 27. It's 27 places to move the decimal here. Right. Oh, I forgot to mention that. You guys see the rule, right? You're going to always move the decimal to the units place. Right. And then it's times 10 to the what?
Negative 27.
Negative 27. Guys, does a negative exponent make the number negative? No. It means you're dividing by 10. That makes sense. Divide, right? Okay. Can you guys do scientific notation? right? Again, much more convenient for your calculator someday. Okay. Here's 1,000 bubbles. So, you guys told me earlier kilo is a factor of 1,000. What about 1,000? Guys, 1 millimeter is how many meters? 1,000th of a meter, right? Oh, here it is, right? Something like that. Okay, there's 1,000 bubbles. Right? You guys got that? How about prefixes? Prefixes. Who knows a mnemonic device for these prefixes right here? King Henry died. There might be different ones. I know. By drinking contaminated milk, chocolate milk, some kind of milk, he dead. So there's from 10 to 3 to 10 to negative 3. Now I want you guys to here's another one. This one's new. Okay. Here's a more expanded list. So I'm going by powers of 3 at a time. So 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12. Right? So if you have 10 to the 3, that's 1,000 something. That's kilo. Right? Guys, what if you have 1,000 thousand? Is that like a million? What's the prefix for a million? Mama. M for mega, right? Like mega Newton, like million newtons. Right? Do this look kind of like computer files, sort of? Computer files? Yeah? Right. Now, technically, computer files are a factor of 1,024. They kind of store these prefixes, so it doesn't exactly align, but right here, right? Because what if you have 1,000 megabytes? You have basically a gigabyte. Yeah, 1,024, but we'll ignore that. Okay? And 1,000 of those brings you to a terabyte. Yeah. Right. So you guys know those? All right. And then you can go the other way. You can go small. All right. So know those. Know your prefixes. Ooh, you guys ready to do some Greek? All right. My earlier AP class, they knew their Greek. I want to see if you guys know some Greek. We're gonna find out. Guys, what is that? Alpha. What is that?
Beta.
Beta. What is that?
Delta.
Delta. Like a change in. It tells you what it is over here. What is that?
Epsilon.
Epsilon. Ooh, nice. What is that one? Oh, you got it. It's Eta. Eta. What is that one?
Beta.
Theta. We were using that yesterday. What is that?
Lambda.
Lambda. Aha, lambda. How about that one? You. How about? Hey, that's what this guy says. How about?
Pi.
Oh yeah. Okay. You guys know pi. Okay. Usually stands for that. What is that one? Phi. Ooh. All right, guys. What is this number right here? This is called the what ratio? Good.
Golden ratio.
Golden ratio. What's the golden ratio? What is this one?
Rho.
Rho. Aha, rho. That was usually used for density in this class. Right? How dense is something? What is that one?
Sigma.
Yeah, capital sigma. Oh yeah, usually a summation. Right? What is that one? Yeah, like a lowercase sigma. Right. Right, yeah. What is that one?
Tau.
Tau. Aha. You'll use that for torque. Torque, like turning a wrench, opening a door. Tau. That one. Yeah, capital omega. How about this one? Yeah, lowercase omega. Okay. All right. Again, that's the whole Greek alphabet, but that's the ones you want to know for this class. You guys good? You guys know some Greek?
It's all Greek to me.
I guess that's good. There you go. Accuracy versus precision. If you want to say how accurate is something, that's like you're getting the correct value. Suppose I have some measuring tool. I have lots of measuring tools around here. And I'm getting correct values. I'll call that accurate. Now, precision is like your, well, in terms of numerical values, it's like you know more digits, right? Like this spring scale looks like I can go to about like 0.1 newtons about precision, right? But what if I wanted even more precision? Maybe I want this. I bet this digital scale can tell me way more precise than the spring scale can, even if they're similarly accurate. You guys think, right? So, for example, guys, see it's lowercase c. Now in physics, oftentimes lowercase c stands for the speed of what? Light. Speed of light. Right? Now, oftentimes I'll say speed of light 3 times 10 to the 8 meters per second, and that's true. But if you want more precision, you say this 3.0 times 10 to the 8 meters per second. Ooh, how about here? 2.9979 times 10 to the 8 meters per second, and then the exact values 2.9979248 times 10 to the 8 meters per second. That's like the most precise. Yep. Yeah. Right. Ooh, let's do some unit conversion. I call this dimensional analysis. Really more than this, right? If you have $1 billion, you spend $1 every second. How much time would it take to spend all the money?
Billion seconds.
True, 1 billion seconds. Right? How long is that? Are you a billion seconds old yet?
Yeah.
No idea.
Am I?
No.
Huh. What's maybe a more human type unit to figure that out? How about years? How about years? Right. So,
Sorry.
guys, the first number on the board is what is 10 to the 9? What is that? Is that a billion? That's a billion, right? And I also attached a unit. You guys see dollars? That's the unit. Guys, in this class, very rarely do numbers not have units attached to them. Right? Almost all the time. In this case, we're going to start off with dollars, right? But don't just write down a plain number. Don't say, oh, the answer is 3 if it's like 3 newtons or 3 kilograms or 3 meters or something, right? Now, you said $1 every second, right? So I'm going to set up some railroad tracks here. Have you guys seen this railroad track method that I'm doing? Probably.
Yes.
Right, so $1 per second. Yeah, so if $1 is like equivalent to a second, then as a fraction, this fraction is basically equal to 1, or number 1 is 1, right? Right. But notice I'm swapping out the unit. Guys, what just happened to the dollars? Go away. Now I have a billion seconds. Okay. Okay. What's a good next unit? Minutes. How many seconds in a minute? 60? Does the number 60 go on top or on bottom? That's right, the bottom. Because it's attached to the unit seconds, 60 seconds. Again, 60 seconds is equivalent to a minute. So as a fraction, this is equal to 1. You're not really changing anything, you're swapping out the units. Right? And notice the seconds cancels. At this point in the process, you would know how many minutes it would take to spend all this money. What's the 60 minutes in an hour? Does the number 60 go top or bottom? Yeah, bottom again. So now the minutes. Cancel it. Now we know how many hours. How many hours in a day?
24.
Yeah, let's go 24. Let's say you're just spending this money. You don't even sleep. You're just spending like Scrooge McDuck. And then let's go for years. How many days in a year about?
365.
365 is called about running. Right. So in your calculator, can you do a billion and then divide by and 60, 60, 24, 365? And it'll tell you. And okay, so your calculator will tell you some number. Take a billion and divide by these numbers down here. Tell you some number. Okay. And guys, that's how many what? What's the unit?
Years.
Years. Yeah, see, years is the only thing not crossed out. Right? So and what's the answer, by the way? There you go. About 31 years. About 31 years. Okay, you guys got that? Okay. Okay. Let's look at a fancier one. Fancy time. Okay. So suppose the energy demand in the States is like 25,000 terawatt hours every year. Okay. Now, even if you don't know what these units mean, if you know this process with the railroad tracks, you can still solve these questions. Right? And let's say the sun is shining, and if it's 12 o'clock noon on a bright sunny day, you're getting 1360 watts every square meter. Ooh, can I start laying down solar panels? Right? But sometimes it's night and sometimes it's cloudy. So let's take an average of about 400 watt per square meter to account for all those. Right? Let's say somehow we're able to store all the energy in giant batteries. Right? One more detail. Our solar panels are 20% efficient. So 100 watts are land in, we only get 20 watts usable, and that goes to a battery that's put on the grid. Right? Now, so we're doing a lot of make-believe assumptions here. Solve a lot of engineering problems to get to this point. Right? In principle, do you think there's some amount of land that could supply the United States energy demand? Right? So we're going to start off with 25,000 terawatt hours per year. And at the end of this process, we're going to get some land area. Do you think you could do that? Right. Okay, so this is a pretty tricky puzzle, but I only got so much class time today, so I might come back to this one in the future. Guys, think about. Let's talk about scaling, but hold on to that idea. Okay, hold on to that idea. I'm gonna come back someday. Scaling. Do you guys see a little tiny box down in the bottom left and a big old crate? You guys see that? Okay. And guys, how wide is my crate compared to my box? It's how many times wide? 3. And how many times deep? 3. And how many times is tall? 3. You guys see that? Okay. Now, when you scale up from this little box to this big crate, different properties change at different rates. So anything linear, as well, you guys just told me 3 times wide, 3 times deep, 3 times tall. Right? What about perimeter? Guys, what if I walk around the little tiny box and then I walk around the big crate? What's the ratio of those distances? Yeah, it's also 3. Yeah, because that's still a linear question, right? Got 4 units versus 12 units, so times 3, right? Right. What about this? What if I paint the front face? You guys see I paint the front face? It took like a gallon of paint. And then I want to paint the front face of the big crate. How many times the paint is it going to take? 9 times. You guys see 9 times on the face, right? Because that's an area question. So it's a linear factor 3 squared gives you 9. Okay. What if these two boxes are separated and I shine a light, the sun's shining, and they're casting shadows? Guys, a shadow, is that 1, 2, or 3 dimensional? 2 dimensional shadow cast on the ground, right? How big is the big crate shadow compared to the little box shadow? 9 times, because that's an area question. 9 times the shadow. Okay, okay. Let's talk about volume. Suppose you want to fill the big crate with little tiny boxes. Box, 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 box. There's a second row and a third row. Yeah, yeah. How many little boxes in the big crate? 27. This is a linear factor of 3, but we're talking about 3 dimensions. Can you fit 27 little boxes in the big crate? Right? What if you fill them with water? Bloop, versus bloop, 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 bloop. How heavy is the big box compared to a little crate? Or big crate compared to a little box? 27 times. 27 times. You guys got 27? Right? Let's do an application of this. What if you have a cargo ship, little cargo ship versus a big cargo ship? It's like 3 times the linear expansion. So the numbers are the same, isn't it? Right? You guys think, because how much water does the big ship face compared to the little ship, like front facing water? Is that 9 times? So it's 9 times drag force. Think of that like 9 times the fuel to send it across the Pacific Ocean. Right? But guess how much cargo the big ship can carry compared to a little ship? 27 times, right? So does it make sense to make the ship as big as you can make it? And right now, the limiting factor is what can you either fit into the port of Los Angeles, or what can you squeeze through the Panama Canal? They just make them as big as they can. Right? Algebra. Can you guys do some algebra? Let's start down here. Is 3 times 8 equal to 4 times 6? Is that the same thing? Same thing? Right? Can I do this? Guys, can I take this 4 and divide it down to the opposite side and make it look like this? Can I do that? Right? Can you do that? Right. Guys, get a real good look at this. Be able to do all this algebra shuffling. You're going to do a ton of it. Can you do letters? Can you do letters? Is that the exact same thing? Same thing. You guys do all these operations. They're all the same thing. Okay. Can you, here's the last thing today. Guys, last thing today. Solve that equation. All right. Here, I'll walk through it with you guys because we got just enough time. We're solving for x, right? At the end of this process, x equals something. What's the first step? Square root. What's the square root of 9? 3 or plus or minus 3. What's the next step? Multiply by 5. What's 3 times 5? 15, right? What's the next step? At 13. What's 15 plus 13? 3. What's negative 15 plus 13? Ooh. What's left then? 7. What's 28 over 7? And then what's negative 2 over 7? Negative 2 over 7. Okay. Guys, if I took either of these boxed in answers at the bottom and I plugged them into this top expression, would they both give me 9 as the answer? Yes, they would. And they're the only 2 that would. Okay. Right. Yeah, that's exactly where I got my morning class. That's as far as we're getting today. So, guys, tomorrow, I still got a few more slides I want to do tomorrow. And I do want to give you guys some more time to work on those trig puzzles. We'll see how this paces out. Hey, you guys have a good afternoon.